Hello everyone. Today I'm going to give you a presentation about the chemical precipitation of copper zinc tin composite oxide for casterite layers. My presentation is going to be 5 sections. I will going to give you a brief information about the casterite-based observer layers, motivation and the aim of the study, precipitation and calcination of the hydroxides, and I will finish with the conclusion. When we are talking about the casterite-based thin film observer layers, we are particularly interested in the solar cells. Casterite-based layers has p-type semiconductor, and also their bandgap is within the promising range for a solar cell material. It has high absorption coefficient, and also it is really low-cost material and environmental friendly combination. When we are looking at the casterite layer, we are taking our steps from an old and important type of observer layer, copper-indium gallium diselenite. They have similar bandgap and crystal structure. However, if you look at the efficiencies of these two different solar cells, you see that there's a difference between their efficiencies. And the reason for that is open circuit voltage results, which is directly influencing the efficiency of a solar cell. And there's a reason for that why we are not able to reach the theoretical efficiency of the casterite layers. It is because of the secondary phases and the crystallographic inhomogeneities. And we are interested in what type of precursor composition and chemical structure we should manufacture that we get the better results. In the literature, we know that stoichiometric values has been better when it comes to photoresponse and solar cell applications through the investigations of the metallic phases. However, at the same time, we know that it's not easy to manufacture the precise compositional that we would like to require, because as you can see in this quaternary phase diagram, we are forming secondary phases that we are not interested in to see in our material. And also second thing is the crystallographic homogeneities. This is also important and related with the compositional values. And therefore, we would like to try something different, and we are interested in co-precipitation of copper, zinc, and tin, 3 of them together, within the desired compositional range as an oxide precipitase. And as you know that there are many studies on the individual single elements, but there are not many studies for the ternary compounds. For that reason, we started our study with the precipitation at different pH values. We filter and write the samples and look at their SEM and XRD, then calcinate them, and after calcination we obtain full oxide material, and we investigated it as well. In this page, you can see the chemical recipe for our precipitation composition, and also the stages that we apply for the precipitation, filtering, and drying process. And in that SEM image, you are looking at the powders after drying. As you can see, we haven't observed many differences. It seems like they have the similar type of particle size in the beginning. And when we look at the crystal structure of this oxide and hydroxide, and we realizing that the zinc oxide has relatively sharper peaks, however, the rest of the copper and tin oxide and hydroxide has broader shapes. One thing we realize is the intensity of the zinc oxide, copper hydroxide, and tin oxide increase with the increasing precipitation pH. After this investigation, we calcinated our powders at 300 Celsius for 3 hours in atmospheric conditions. As I mentioned, the composition is really important for us, especially the composition of the cations. Therefore, in the table that I'm going to show you, I am going to give you the information about the cations, the normalized version without any oxygen and sulfur. As you can see, we have the stoichiometric values and some of the high efficiency precursors from the references, and also we have the results for our compositions when it is the pH 6, 8, and 10. And in all samples, we were able to reach the copper poor results. But when we look at the zinc to tin ratio, what we see is slightly tin rich results. However, we are really happy with the results that when we have the precipitation pH 8, it is copper pure, and also we got the results close to stoichiometric value when it comes to zinc to tin ratio. And the structure of this material after calcination is they are all oxides. We observe oxides for all of them. And the intensity of the zinc oxide increase, if we compare before and after the calcination, this suggests that the particles get bigger for the zinc oxide. But on the other hand, we haven't observed any dramatic increase for the copper oxide and tin oxide size especially. And this is suggesting that we got the smaller range of particles for the copper and the tin oxides comparing the zinc oxide. So let's have a look at the morphology of our samples. We are looking at all the pH values, and one thing catch our eyes is the two different regions for the pH 6, and also another thing is the particle size got smaller with the increase in pH. So turning back to this pH 6, we need to apply something different to understand what's going on in the pH 6. And when we look at this SEM image, we take it and we apply some EDS layered mapping process to understand which compositions we are looking at and what is happening. And the first region that we are interested in is this white circle region. And the second part is that I'm going to show you with the yellow rectangle. And in this colorful images, you are seeing the single elemental EDS layer mapping corresponding to this first image. And as you can see that the zinc, oxygen, and sulfur is giving brighter and more intense signal for the bigger particle region. And when we look at the yellow rectangle, we are still seeing some of the signals corresponding to zinc, oxygen, tin, and copper. And this means that in these regions, we all have the zinc, copper, and tin-based oxides. And also in the large particle region, we have the large precipitates of zinc oxides beside a passable phase that contains zinc, oxygen, and sulfur. With this, I would like to conclude that the chemical precipitation of copper, zinc, tin oxide, and hydroxides has been performed at different pH values, and we obtain zinc oxide and copper and tin-based oxide hydroxide, the combination of them. The calcination process increased the crystallinity of the zinc oxide and transformed the copper tin hydroxide to oxides. And according to EDS mapping, we have zinc, oxygen, and sulfur-based phase. And the composition of the powder after calcination is copper pure and tin rich, with a promising compositional ratio for the precipitation pH 8, which is copper pure 0.87 and zinc and slightly zinc pure 0.92. According to EDX mapping and XRD results, we conclude that the copper oxide and copper tin oxide have smaller grain size comparing to zinc oxide. And we are really interested to sulfurize the samples and investigate what type of behavior they are going to show in our future studies. Thank you for your attention, and you are welcome to ask me any questions and connect me on LinkedIn. Thank you.